Thanks so much for the organizers first for letting me come and talk about something that I really love, high K magnetized modes in MHD turbulence and MHD dynamos. And thanks also to the hot tub organizers at the Best Western. They've been doing a really great job keeping the hot tub nice and warm every night for Ashley and I to talk about science. So this science, of course, isn't done by myself. It's done with these fantastic collaborators, in particular Nico Creel, who's at the Australian National University. He's a graduate student doing really nice work on turbulent dynamos. So really I have a fluctuating display system that's probably undergoing some kind of turbulent cascade. No, really I have 3 goals this morning for this very early morning talk. The first goal is to wake everyone up, which is very easy because I'm a very loud Australian. The second goal is to grow a small-scale kinematic and nonlinear dynamo field in this KIPP theater. And my third is to venture into the dynamo saturation with these big turbulent boxes that I've been doing for the past couple of years, reaching up to 10,080 cube domains, which is Reynolds numbers of close to 10 to the 6 or so, to resolve the inertial range of MHD turbulence in an asymptotic state. Cool. So no, there is essentially a chronology to the way that magnetized high K modes exist in turbulence. So you can start off with a very weak seed field. So that is the integral over your power spectrum of the magnetization is very small compared to the integral of the source that's driving the turbulence. And at some point you're going to go through a very dynamic stage called a dynamo. When we're initially growing magnetic modes, growing essentially these high K modes in a turbulent soup, it undergoes a number of different phase transitions. The first phase I'll talk about quite a bit today. It's a kinematic dynamo. It's the fastest growing phase. Then you get into a secular growth regime, this nonlinear dynamo. And finally you get into driven turbulence where you're in a stationary state. And then if the source function turns off, just as it did right now, you get into a decaying state, as you can see over here. Now, for a theorist, it's actually really frustrating because these are not necessarily the same theories that describe all of the different phases. The same underlying theoretical frameworks do not actually describe all of these different phases. We do not have a smooth set of theories that evolve into one another. We have a set of Cosenza theories, Karlsgrad and Anderson theories for the kinematic dynamo. We have some beautiful nonlinear theories for the secular dynamo. We have some driven turbulence theories. Oh my goodness. Probably a lot of theories that people have heard before of driven turbulence, Goldreich and Schroeder, Bolder's dynamical alignment, Galtier's fast magnetosonic wave turbulence, etc., etc. And then we go to the land of decaying turbulence, which is described by a set of rugged invariants. Don't fit well together is my whole point of this exercise of drawing this diagram. But today we're going to be looking at a particular place in this theoretical landscape just about here. And this is, we're going to go through the phases of the turbulent dynamo, the kinematic and nonlinear, and then we're also just going to venture off this cliff here into driven turbulence and see what it looks like. And this will be the case for no net flux. So you can see also that I've painted on that these theories are quite different because you're actually doing different things with the large-scale properties of the magnetic field. So a lot of driven turbulence theories are with net flux, have a guide field penetrating through the system, and a lot of turbulent dynamo theories are actually no net flux systems. So it's not clear how these two things exist together and if there's any universality at all. So what is a magnetic dynamo? A magnetic dynamo is a process where you have an energy reservoir and you have a magnetic energy reservoir, and there's some coupling between the two. The coupling usually looks like this in Newtonian MHD equations, and you have some energy flux that moves from the reservoir into your magnetic reservoir that ends up growing it. It ends up growing it, and if this growth is larger than the resistive decay out of that reservoir, i.e. that the magnetic Reynolds number is larger than some critical value, you will continue growing it until you get into a back reaction state. And the back reaction is just when the U, the velocity, the thing that's coming from this energy reservoir, is a function of this now, okay? And this will get you into a secular growth state. So you will eventually get into a steady state where, of course, all these fluxes are kind of matching and equal, and this is then driven turbulence. Now we see these dynamos, these kind of small-scale turbulent dynamos, everywhere in the universe. It doesn't matter where you look, you find them. So this is an example between two merging neutron stars. You see it undergoes, this is the integral magnetic energy on this case, on this side, and this is the time before the merger. And you see the magnetic energy just increasing exponentially, pausing for a bit, exponential again, and then doing some secular winding. These two exponential growth stages are actually the growth of high K modes in the system. They are a small-scale dynamo. And we'll talk a little bit about the neutron star case. You can go to much larger scales. You can kind of do your convolution over an entire galaxy in these cosmological simulations. You can track their magnetic field as a function of redshift or a function of time. And you find, again, this beautiful exponential growth. The secular growth here is the curve itself, because this is plotted in log linear, so the secular growth actually looks like a curve here, and then you get to a saturation. So an entire galaxy has a small-scale dynamo, birthing high K modes. You can go to the molecular clouds in the first generation of stars, the intracluster medium, the cosmic filaments. It all looks like a small-scale dynamo on a particular set of scales. Now, it doesn't matter. I was just showing you a whole bunch of MHD regimes. It does not matter what regime you're in. Here you're in a weakly collisional Brzezinski MHD model, exploring the nature of how the Brzezinski fluxes change the dynamo. It doesn't actually do very much. Here, Lorenzo, if he's in the crowd, there's Lorenzo, has done this beautiful work on magnetogenesis coupled to a MHD dynamo in the completely collisionist regime, again showing lots of these universal features, these very fast growth stages into a secular growth, into a saturation. The dynamo is ubiquitous. The small-scale dynamo is ubiquitous. And it's because it relies on simple ingredients. Ingredients like a stochastic velocity gradient tensor. The more stochastic, the larger the Lyapunov exponents of the tensor, the better. And high RM plasma, which of course we find everywhere throughout the universe. Here is the critical RM for the small-scale dynamo across a variety of magnetic Prandtl numbers. So you can see you excite dynamos at very low critical magnetic Reynolds numbers. They are easy to excite. So I'm going to be going through the chronology, and in doing that, I'm going to be talking about a lot of simulations. I'm not going to go through any one particular simulation. I think this talk I tried to count has maybe 400 or so turbulent boxes across a huge parameter space. So this has been years of just running turbulent boxes across different Reynolds numbers, different Mach numbers, all this, and we've just built up a beautiful data set to test dynamo theories in a lot of detail. So nothing fancy here. These are just your classic turbulent boxes undergoing dynamo. What that looks like, if I just track so this is the Mach number of the velocity fluctuations, not any kind of bulk Mach number, but actually the rest rate Mach number of the fluctuations. This is what it looks like when you track it across time. You get it very quickly into a steady state turbulent regime. That changes a little bit if you're in different dynamo regimes. But all I want to show here is that we're spanning across essentially subsonic flows, which are pretty much incompressible, to supersonic flows, which are very, very compressible, rich with compressible modes and density fluctuations. And these are mostly the numbers that I'll talk about to parameterize the different simulations. So I hope everyone is a little bit familiar with these numbers. I know the collisional folk will be, or the collisional folk will be like, what are these? Well, you know, you can do some coarse graining. You can get these out of a collisionist plasma. It's not too hard. So dynamo. This is what the classical dynamo plot looks like. This is the magnetic energy density over the kinetic energy density. And you can see now that these simulations, which I was showing you the Mach number before, undergo a tremendous amount of magnetic energy growth. And they go through those classical phases that I was just telling you about. They go through the kinematic phase. They go into a secular phase. This is just a zoom in of exactly this corner here. You see that it goes through essentially a linear growth stage and then into the saturation. So every simulation that I show is going to be going through this phase. And we're going to be essentially focusing on statistics in each one of these phases in different parts of the talk. Okay. So we have to think a lot about in case-space. Dynamo theory is a case-based theory. And we also have to ask the question, if we have a cosmograph cascade setup or some kind of cascade setup, and I put an initial magnetic field at a particular K, does it matter? Does it change the dynamo? This would be very nasty if it did. It means that the parameter space opens up, everything depends upon my initial conditions. I don't want that. So what we did, we played around with the different K-space structure here. So you can put a magnetic field with the so-called Kazantsev spectrum. You can put a magnetic field just on the driving modes. You can put a magnetic field just at the K equals 0 mode, a mean field. and you can show that everything looks exactly the same as long as you integrate it for long enough time. So the saturation of the dynamo and even the growth rates exactly the same. All the seed field does is just give you some kind of offset. So what about if you do something else? What about if you actually you fix your k-space structure and then you just change the amplitude? Well, actually exactly the same thing happens again. The dynamo is universal to both seed field amplitude and seed field structure. So you can decay into the same saturation that you would grow into. This is beautiful. This is a beautiful aspect of the turbulent dynamo. Very, very universal in the way that it saturates a magnetic field and holds it at that saturation. Okay, we were looking at this plot. We were a bit concerned about this, but now we're not. Now, over very, very short timescales, as soon as that magnetic field couples to the viscous, or couples to the velocity gradients in the plasma, it will shoot across k-space. It'll shoot across k-space, and the peak scale of the magnetic energy will essentially grow exponentially. The width of the power spectrum function will grow exponentially, and the integral of the power spectrum will grow exponentially. This is a very exponentially growing process. But what about the growth rates? What about this? What is that gamma? I want to quickly point out that we see this in simulations, exactly as I'm painting it down in the cartoon. We see this in actually KHI dynamos that are relevant to neutron star mergers. We see this beautiful shift of all these high K modes really, really fast early on in the simulations, where you're getting this really, really fast exponential growth. So this is kind of a signature of the kinematic dynamo. So what is this gamma? What is the growth rate of the kinematic dynamo? Well, just from essentially twiddle algebra, you can kind of get at that. And all you're saying here is that the velocity gradients that are essentially the engine of the dynamo are really set by the small scale structure and the turbulence. And that is the viscous eddies have the shortest turnover time, so they're really going around really fast, but also they have the largest gradients as well, which just comes from cosmograph theory. So for a spectrum that looks like a cosmograph spectrum in velocity, this is exactly what we expect the growth rates to go like, RE to the 1/2. And for a different spectrum, a spectrum maybe that is supersonic and has a K to the -2 spectrum, potentially just from shocks in the medium, you get something like RE to the 1/3. Now we can test this, but it's hard. And it's hard because these are fluctuating systems that, have RMS fluctuations that scale with the velocities of the systems. So what you actually have to do, every point here is 10 simulations that have different random seeds and the ensemble average over the random seeds to get good statistics so you can measure these growth rates as well as possible. And what we find in the subsonic regime up here, RE 1/2, perfectly beautiful, and down here RE 1/3, exactly as you'd expect for the dichotomy between a cosmograph spectrum and a Burger spectrum. So this is crazy. This is a fast dynamo. RE is what the growth rate depends on. That's insane. So you can actually kind of, do some twiddle algebra here. You can get an RE, an effective RE for neutron star mergers based on essentially the weak interaction setting a bulk viscosity, which ends up being similar to a shear viscosity, which I showed just recently for the dynamo. And that means that gamma here is 10 to the 3 meters per second. Millisecond per millisecond. And the simulations, the global simulations that do the neutron star mergers, get about 2. So this tells you immediately that the growth rates that you're going to be seeing in global simulations for this kind of process are incredibly under-resolved. And everyone who's worked on small-scale dynamos knows this already, right? These are fast. You will never get growth rates like this because you do not resolve the correct viscous scale. And the dynamo is set that the engine of the kinematic dynamo is the viscous scale. Okay, so what did I want to say here? I'm not too sure. But let's go here. So we can also talk about the separation. So this power spectrum is crazy. It's peaking at the smallest scales in the system. And in fact, it's peaking at around the resistive scale. But you can ask, how long is this interval? We call this the subviscous range of scales. And with quite simple twiddle algebra, again, you can get at the separation scaling like PM to the -1/2 or PM to the 1/2 in K-space. So the separation, the actual length between the viscous scale and the peak scale of the magnetic energy, where all the magnetic energy fundamentally relies, is a function of PM, of course. So we want to test this relation. Essentially, we have to go to our direct numerical simulations. We have to measure viscous dissipation scales. This is not too bad. This is quite easy, actually. You can do this through the rate of strain tensor spectrum. You can then, all I'm saying here is that every point, again, we want to get rid of our grid. We essentially are very worried about how the grid numerical effects are going to impact our dissipation scale measurements, which is absolutely true. It is actually really, really quite hard to get rid of any numerical effects from diffusion. So every single point here is many simulations. Each one of these simulations is done at a different resolution and then taken to the infinite n-grid limit. So we essentially do some Richardson extrapolation for every single data point here. And that's why this plot alone is 200 simulations. So these are very precise measurements, is what I'm getting at. Now, when we actually test this PM1/2 relation, which is kind of it tells you about the structure of the kinematic dynamo, this looks very beautiful. And it looks beautiful for subsonic simulations. It looks beautiful for supersonic simulations. It works across the board. So this is telling us that our peak scale, the peak scale of the magnetic energy, always goes all the way down to the resistive scale. So this should also worry global simulators. They do not even have these scales. These scales do not exist in their simulations. And yet that's where all the magnetic energy resides. I notice that I have around 10 minutes and I'm barely through my talk. So we talked about, this is the kinematic dynamo setup. You have the engine here and you have the peak energy here. But, you know, if you go to any observation of a magnetic spectrum, it could be in the solar wind, it could be magnetosheath, it could be interstellar medium, it could be anything. The spectrum look like that. They do not look like this. Kazantzov is not the spectrum that we observe in nature. So we have to essentially turn this spectrum into that spectrum. And this is like quite an interesting phase change in the entire magnetic structure. And the way to think about this, at least what's being proposed, is that you get into this phase transition as soon as you get into your integral energy equaling the viscous scale eddies. And then there's some back reaction on that eddy, and you keep traveling up and up the spectrum like this. There's the back reaction moves to larger and larger scales, lower and lower K modes, and eventually you get to something like this. And you can make a prediction for, if that's how the back reaction works in terms of integral energies, then you expect that the energy the energy growth, so the Emag is proportional to T, goes like the energy flux here. So this is the energy flux rate. In other words, the turbulence is essentially acting as a reservoir, and the magnetic field is just grabbing energy flux directly from the cascade. And it does that and moves up into lower K. Now, this is the first measurement, I think, that has been done to actually confirm this theory. It does indeed work. This is, again, a very, very hard measurement to do. Every point here has to be many, many different statistical realizations averaged over so you can get this beautiful data. But this looks very good. So we think that this kind of idea of the secular growth stage just being essentially parasitic to exactly the energy fluxes from the cascade in this linear fashion works very, very well. So this is very cool. And this is much slower now. This is actually much slower. So the kinematic dynamo very, very fast. The secular growth much, much slower. So yeah, if you were just taking pictures of the universe, you'd kind of expect to see a lot of this and a lot less kinematic. So now we're moving here. So we've kind of walked our way through the kinematic and the nonlinear dynamo, at least to a certain degree. We haven't really talked about the K-space structure so much of the nonlinear dynamo. We'll actually get there a little bit. But now I want to walk into the driven turbulence state. And this was a paper that I just put out recently in Nature Astronomy. I actually just found out a couple of days ago that it made the cover, so it looks very pretty. If you're into turbulence, I feel like this is a big win. Getting turbulence on the cover of Nature Astronomy, very cool. Doesn't happen so often. These are big 10,080 cube simulations, and essentially the goals here for running these big simulations was really just to understand the underlying spectral structure of the turbulence in a regime that is very, very compressible, so a supersonic regime. Also, we wanted to understand dynamo saturation in this particular supersonic regime as well. These are pretty big simulations. You have to run them on around 150,000 compute cores for around 80 million core hours to even do anything useful. And even that is actually not so much. So you actually generate a lot of data. So you're dealing with around 3.5 petabytes of data by the end of your simulation, and that is itself challenging to deal with. And the way that you have to do this is you essentially, here I'm just plotting Mach number as a function of time. You run some smaller simulations, 2000 cubed. You run it through the whole domain, and then you just pick out patches. Here I'm essentially grabbing the 2000 cubed data. I'm extrapolating it to larger scales, or rather interpolating it, inwards, to get 5000 cubed and resetting there, and then I do that again for 10,000 cubed. And it's just to avoid this. This burn-in phase is more expensive than the entire time that we can run this. So it's impossible to start this with stupid initial conditions, in other words. Now, you get a rich set of dynamics in these simulations because they are supersonic on the outer scale. And so on the low K modes, you have completely supersonic dynamics in these simulations. So this is the K space, this is the wave mode, this is the velocity dispersion on that wave mode. And essentially you transition into a set of subsonic dynamics. And you go past this scale that we call the sonic scale. And this actually does set up a dichotomy of dynamics that we'll talk about a little bit soon. There's another scale here that we resolve very well in our simulations, and that is, of course, the alphanic scale. So the alphanic scale, at least in my language, is very similar to the energy equipartition scale. And essentially, you go through a transition in K-space. Again, I'm plotting this in K-space, where you are kinetically dominated. So you're dominated by the kinetic motions on the outer scale. And of course, these are supersonic. So you're kind of in this very supersonic kinetic energy dominated regime. And then you go to small enough wave modes, small enough scales, high enough wave modes, and you get into a magnetically dominated regime. So you have multiple regimes in a single turbulence. You have supersonic, kinetically dominated, and then you go down to the subsonic, very magnetically dominated K modes. And you do see different signatures for this everywhere. So here I'm showing the energy spectra. And I want to highlight that these are very disparate spectrum. They don't actually look the same. This is the magnetic spectrum. This is the kinetic energy spectrum. There are two power laws in the kinetic energy spectrum. One we think is the K to the minus 2 Burgers type turbulence on the outer scales. This is just all the shocks developing on the outer scales. And then you get this actually really beautiful extended K to the minus 3 half spectrum on the small scales. And I just want to remind you that this is no net flux, so it's not exactly obvious that we should be applying ideas from dynamical alignment, but I'll show you that you can try to apply these and see how they work. And then the magnetic energy spectrum, very, very different. There are a whole host of different models for this magnetic energy spectrum. Essentially, it is none of them. And what it is this kind of empirical relation found back in 2023, K to the minus 9/5. So it's kind of not as steep as these reconnection tearing mode spectra, but it's not as shallow as your classical turbulence spectrum. Very interesting. And this power law in the magnetic energy spectrum you only really start resolving at very high resolutions. You can see, thank you. You can see that this is 2,000 cube, 5,000 cube, 10,000 cube, and you can see it really becomes perfectly or a little bit self-similar at around 5,000 cube-ish. Now you can do transfer functions. Transfer functions are amazing tools for actually working out in K-space if there is a cascade or not. These are just computing the energy fluxes between different K modes in your turbulence. And if you have a local cascade, it's going to look exactly like this beautiful diagonal around the central K mode. And it's going to be blue on this side and red on this side, which means a cascade moving this way to higher K as you go up there. So we see this quite non-local mixing supersonic shock stuff on the low K, and then you see this beautiful direct cascade into the high K as you get into the subsonic cascade. You can also see that the magnetic energy spectrum is really getting, the outer scale is really here at the energy equipartition scale. So this is where you get coupling between the velocity gradients and the magnetic field in this driven turbulent state, in the state of saturation. So this is very cool. You get to see lots of nice things from this plot. So I want to focus on the incompressible spectrum in 5 minutes, or 4 minutes now. It's K to the minus 3 halves. This is interesting. What this means is that there is some mechanism that's depleting your nonlinearity. So this is kind of a strong nonlinear case, the K to the minus 5/3 spectrum. And then the idea here is that if you want to make this K to the minus 3 halves, you have to deplete the nonlinearity in your equations to essentially try to shallow the cascade a little bit, let it hang on to its energy for a little bit longer. One idea here is that you can do this through aligning U and B. This is a very alphanic incompressible idea, but we are in the incompressible cascade, so we may be looking at alphanic turbulence. And essentially what you can do is you can just align U and B in a scale-dependent manner that conserves your energy flux. So you go from the Goldreich-Schroeder to the Bolderev case, and what you expect in your turbulence is just alignment, scale-dependent alignment. And you see from the field here that is a beautiful patchy U dot B field with these huge regions of very, very strong alignment. The alignment is in fact too strong, I would say. Very, very patchy cellular turbulence, which I think is very important for the dynamo saturation. Here, I'm not going to talk about this, but here you can actually compare with Bolderev's theory. You can get into the local frame of the magnetic field. You do all the structure functions in that frame. And essentially what we find is that the scale-dependent alignment is weaker than the prediction from incompressible turbulence or reduced MHD. So we find something like this instead. So this is a scale-dependent alignment, a process, but not the Bolderev picture. Now, what is very, very interesting is if you look at these patches again, but you go from the kinematic to the nonlinear and saturated state. And what you find is the U dot B patches go from being very, very small and fluctuating, looks like a random Gaussian field almost, to very, very coherent and large scale in the saturation. So these patches are kind of growing larger as you go through the nonlinear state. So the nonlinear state is in some sense giving rise to very, very aligned turbulence. And you can actually see this in K-space as well. Here you're looking at the thank you. Here you're looking at the spectrum of that alignment, the spectrum of cross-helicity. And you can see that as it grows through the nonlinear state, it back reacts on the total energy. So this is the total energy spectrum in yellow. And you can see as it grows, this is the onset of the nonlinear state right here. The back reaction modifies the total energy exactly by the cross-helicity. So this is fascinating and something that we're trying to understand better. And this is really seeing in K-space the growth of those patches. So now in my mind, what you are seeing here in the nonlinear state is actually the patches growing to be larger and larger, and as the patches grow, the induction turns off on the scale, the patch scale. And as you go up and up the cascade, you're just turning off the induction on larger and larger scales until you reach the outer patch scale, and then that's where your induction is turned on again. So you drive the magnetic turbulence at the outer scale of the patch. And that's what I have here. So I'm not going to say much more than that because I think it's very interesting. If you wanted to chat to me more about the details of that nonlinear dynamo state, let me know and we can chat. But I think there is a lot of work to be done here in terms of understanding how a system relaxes on a K by K mode basis. So let me just put up my conclusions here. Kinematic and nonlinear theory at the level of the integral energy works very, very well. Everything looks great, with subtle changes based on if you're in a supersonic or subsonic regime. And then the scale-dependent alignment is very, very cool in the saturated state because it's been completely motivated for alphanic nonlinearity suppression in incompressible turbulence, but it ends up playing a very important and potentially generic role in saturating the turbulent dynamo. And that's what I'll leave it as. Thank you very much.
Thank you for your talk. Any questions? Dimitri?
Thank you. Thank you very much, James. Very informative and interesting and insightful talk, and yet very clear. A lot of information, but very clearly. So I would like to compliment you on this. I have two questions.
Yes.
One is a quick technical question. In your supersonic turbulence simulations, how do you deal with thermodynamics? Is it isothermal, or what do you do with energy?
Yes, so at 10,000 cubed, you don't want to be actually dragging around any extra fields. So we have just set it to be isothermal. And this is well motivated in the cold molecular ISM, but maybe not well motivated elsewhere.
Okay, fine.
Yeah,
fine.
yeah.
That's great. Fine.
Yep.
So that was just to clarify. And the second question is, again, in supersonic turbulence, there is a sonic scale.
Yes,
right?
yes.
And then there is a scale at which magnetic energy density becomes equal to the kinetic energy density.
Yep.
What determines the ordering, which one is larger, which one is smaller, and the ratio between them? Is it always, one is smaller than the other, or it depends on various parameters?
Well,
is it a factor of, does it scale with Mach number, or what's going on?
Yes, so the sonic scale scales with Mach number. It actually, in k-space, it goes like 1 over Mach squared. But the relationship does not, well, the energy equipotential, I think you can actually, you know, I'm just thinking what you can do with large-scale magnetic fields. I think it's always going to be larger than sonic. Yes. But, you know, so there's an alphanic Mach number scaling of the energy equipartition scale and a sonic Mach number scaling with the sonic scale. So I think you can play around with your alphanic and sonic Mach numbers to mess around with this, but I also think that just the underlying k-space structure of the magnetic field is always actually going to put that on larger scales than ks. So with respect to the large-scale field, I think you can move around the scale as k equipartition a lot, but with respect to the underlying turbulent field, it's always going to grow into around the sonic scale-ish. It's always going to be around there. But I can't tell you definitively. By factor of a few, exactly. Yes.
There's a question from...
But it's actually quite interesting because when you plot the magnetic energy density over the kinetic energy density, you see that the sonic scale has the most magnetism. It's actually the peak of the magnetism. So I show that right here. Yes.
Okay, there's a question from Lorenzo.
Great talk. Apologies if maybe you touched on this already. Can you comment on how the various thresholds maybe for driving a dynamo, not driving a dynamo, will depend on the ratio of compressive mode to solenoidal mode of the outer scale?
So things do change because I kind of have talked about a very vanilla case here where you're driving with solenoidal modes, but the growth rates change and the saturation changes when you change around your solenoidal versus compressive mode driving. Critical magnetic strength? No, I don't think that changes at all. No, that doesn't change. But let me just think about this for 1 second. I think if you go to high enough resolutions, you can actually get back universality, even if you are driving with different ratios of solenoidal and incompressible modes. It's really, the compressible modes, the role that they play in a lot of these simulations is that they change the large-scale structure. And they decay very quickly as well. Decay very, very quickly, change the large-scale structure. But as soon as you get into the subsonic rate, as soon as you start resolving this subsonic cascade, it doesn't really matter what your large-scale structure is doing so much. Yes. So I don't think it would matter. Chris?
So on small scales, a high Reynolds number, you're quickly reaching equipartition.
Yes. I mean,
but
right here.
then, how close is one to understanding the Reynolds number scaling of the time scale for you to reach equipartition on large scales?
So you're talking about the large-scale dynamo now?
The migration of the power spectrum to large scales, low K.
I think we're pretty far away from that. The large-scale dynamo is a mess, right? You know, I'm talking about these chaotic high K modes. The whole large-scale dynamo theory is like that. It's a similar chaotic mess in my mind. Okay. Yeah, because you can have shear current effects, alpha dynamos. I mean, this all then starts depending upon the large-scale structure very sensitively. Yes.
I have a question about the saturation. So you mentioned the nonlinear saturation. You kind of progressively, had a nice plot of
like this.
Maybe before that, but we're basically where the velocity fluctuations align with the magnetic field. And
Yes.
Patches where the induction doesn't work.
Yes.
Do you also get current aligning with B in the kind of local force-free states? Can you comment on?
What a fantastic question. I think I have a bonus slide. Yes, so you've probably seen this plot before. The question was, do I get other alignment? I talked a lot about U and B alignment in the saturation. Do I see other alignment? Yes, I do. And this is very suspicious of a relaxation process. Now that you see the full picture here, you're seeing U and B alignment, so alignment between the velocity and the magnetic field, B and J alignment, J here is the curl of B, and U and omega alignment, where omega is the curl of U. And so, you know, essentially if you ask the question, what is the minimum energy state for the system if I conserve magnetic helicity and cross helicity, this is it. This is it. It wants to align all of these vectors, which actually take your nonlinear MHD equations and make them linear hydrodynamics equations. It's insane. The saturated state of the dynamo wants to become a linear hydrodynamical set of equations. So alignment everywhere, across all primitive variables and their curls.
Yeah, there is another question here.
Thanks. Yeah, Dimitri. I'm wondering about, like, in a lot of astrophysical systems, you can imagine having driving at a lot of different scales, for example. How would that affect your results, or would it even matter?
It's okay.
Driving at all different scales will affect these results because the dynamo struggles to saturate at scales where there is being energy injected. So this is just kind of true no matter what you're doing, no matter what regime you're in. If you're driving subsonically on the K equals 5 mode, the saturation will come up before the K equals 5 mode. It'll get saturated. So it does depend on how you drive and where you drive in K space. So that's all I'll say about that. But it is interesting. We set up these ideal simulations so that we can learn about the simplest case.
I have a question more. So in some astrophysical environments, radiation can play an important role.
Yep.
So how dynamo changes when a radiative environment is at play?
Yeah, I mean, so the coupling is going to be through the pressure, obviously, right? And I would say that the pressure plays a minor role here, in general. And you can play around with different equations of state, which could be potentially an equation of state that kind of looks radiation-y, like a 4/3 kind of equation of state. Just looks pretty similar. It's not super sensitive to what the equation of state is doing.
But are there any simulations that confirm
so.
this intuition?
I don't think so. I don't think so.
Thank you. Thank you. Just on this very interesting slide, I have a number of questions, but one of them is this. If you throw away magnetic field, that means if you just go to hydrodynamic and compressible hydrodynamic turbulence, presumably much more is known about that. In particular, one can make measurements, laboratory measurements in water. Do we see Beltramization?
Certainly in the supersonic case you do.
In the supersonic?
Yes, yes. And I think there are a lot of, this is vortex tubes, right?
Right.
Yes.
I was thinking of incompressible.
Yes.
Water.
Incompressible, I'm not sure. I mean, I work a lot in the supersonic realm. But certainly in in just hydrodynamical supersonic turbulence, you see this as well. Yeah.
Thank you.
Yeah. And this is, of course, actually, when you write out the turbulent nonlinearity, this is one of the components, because it has a lambda vector in it, so it's actually reducing the nonlinearity in the hydrodynamics as well.
I have a question here, yeah.
Yes.
So I want to just make sure I get a picture about neutron star merger situation, KHI instability, how the B field play a role. What you're saying is that currently you cannot resolve the fast growth phase.
No.
Numerically, right?
And I didn't even talk about the saturation.
And then there also, even if you resolve it, then you have to go to larger scale. But then, so what's the current story of how important this KHI instability?
Well, the current story is
in light of your understanding of what is.
So the current story is that the KHI dynamo is a very interesting dynamo. It's not purely a small-scale dynamo. It has a large-scale dynamo feature as well. And I put it here, so I said exponential growth pause, exponential large-scale dynamo, but it's actually here as well. It's actually everywhere. The magnetic flux can tap into the free energy of the mean shear layer, and it can do that very effectively. So it's creating all these fluctuations, it's creating a turbulent slope, it's growing the high K modes, but it's also tapping into just the shear layer itself of the KHI, and that can grow a colloidal field fast in local boxes. Yep, but this, this is something that scales with Reynolds number. So, this is fast. This is very fast. Like I was showing before, right? The Reynolds numbers of these systems, if you just use the bulk viscosity from the weak interaction, is actually very large. And all of these initial processes, so these are essentially all growing the high K modes. Here I have not showed growing the large scale field as well, but it looks very similar. You expect theoretically to get something like this for your growth rates, but the simulations have something like 2. So there's a huge discrepancy between what you can do locally and what you can do globally. That's what I'll say. I think yes, I think connecting the 2 scales is very important, because this will grow a colloidal field really quickly on the scales of the viscous scale, or on the time scales of the viscous eddies. Yes.
Okay, so in like PIC simulations of turbulence, you often see the turbulence driving reconnection. But I don't think you would see that in your simulations.
So say again, sorry. In PIC simulations,
PIC simulations of turbulence.
Yes.
You see often turbulence driving reconnection. And
oh yes,
so
yes.
Do you?
No, you see that.
You see that in your simulations?
Oh, absolutely.
What's the effect of that? I guess
the effect. I mean, what's the effect is a good question. It's not obvious. I think this is probably the best plot, but these are actually current sheets. This blue stuff down here is current voids, and this red stuff here is actually current overdensities. And in these current overdensities, there are just sheets everywhere, and they're tearing unstable at these resolutions. So you get tearing modes, you get plasmoids everywhere. And the question was, do these impact something, a global statistic like the power spectrum? There are predictions for how they should modify the power spectrum, and this is kind of what I was showing here. These are 2 theories or calculations or theories that show that the power spectrum should be, or predict what the law should be for the power spectrum if you modified it under a process like fast reconnection. And we find that, at least in our power spectrum, we don't see those signatures. Does that make sense? We think that there could be, if you go to large enough grid resolutions, a set of scales that are influenced by the cascade that's being set by reconnection on at high enough K. So that's the idea. So you have to get into this asymptotic regime where there's tearing modes popping off everywhere in your turbulent box. Very tricky to do. You have to go to these 10,000, 5,000 cube simulations. But in terms of this statistic, which you have to think about power spectrum as averaging over modes, you're integrating over all these modes, so you're getting some average set of dynamics, or statistics. In terms of this, we do not see that imprint on the spectrum. In terms of going into the box, locally computing reconnect, we see imprint everywhere, right? It's happening locally everywhere, we see it everywhere. It's not just a PIC thing.
About Beltramization.
Yes.
I'd like to offer my kind of understanding, and if it's correct, tell me if it's correct.
Please go ahead.
So in incompressible fluid, there is no energy principle, and the only thing that incompressible fluid can do is a cascade, turbulent cascade. So there are Beltrami states, but they're not attractors, so to say. But in MHD, there is Voltaire-Taylor principle which is almost like Beltrami states. For the current and magnetic field. That says that those states are preferred to some other configurations. And here it looks like you're suggesting that it's kind of double Beltrami, both in the fluid velocities and in current magnetic structure.
That's right.
Is that correct interpretation?
It is actually an expectation. I was trying to see if I had my the correct slides, but I don't, unfortunately. So the way that at least I think about Beltramization and why it's almost inevitable here is I'm not thinking about hydrodynamics necessarily. I'm thinking about what is the minimum energy state. So I want to build up a functional of total energy, just constraining the invariance of the ideal invariance of MHD, and that is cross helicity and magnetic helicity. And when you do that, and you build up that functional, you minimize it, the states that you get into are Beltramized states. That just comes from vanilla ideal MHD invariance. So Beltramization is a natural consequence of minimizing your energy whilst constraining your magneticity and crossalicity.
Okay, we have time maybe for a very, very quick question. We can ask it. Okay. Okay, we should thank our speaker.
Thank you very much.